this is going to be like a quite technical deep dive into procedurals. So what are procedurals? Procedurals are this nice way in Notch that you can generate meshes, volumetrics, and so on by combining different shapes like primitives and fractal noise and particle blobs. And you can use Boolean operations to combine them together. And you can clone them and repeat them stuff. And you can use them to generate meshes and so on. So that's what procedurals are. That is not what procedurals are at all. What procedurals really are is signed distance fields. So a signed distance field is basically a signed distance function describes a signed distance field. And a signed distance function says, give me any point in the world in space, and I will tell you the distance to the surface, wherever the surface is, wherever the point is, wherever the surface is. And it's a positive value when it's outside the surface, and it's negative value when it's inside. And this is super powerful, because they have some really useful properties that make them useful across a ton of different things. So roughly, a really poor diagram that shows what a signed distance field kind of looks like. So I've got a bunch of red points in space, and the circle around the red point is kind of showing the signed distance. So for a point in space, you can see that that's the kind of distance to the nearest point on the surface. And the blue one is inside the surface, and the red one's outside. So why would you want to do this? The thing about signed distance fields is that you can use quite simple mathematical formula to generate really complicated things. And the size of them and the complexity of them is unlimited. So you can have something that's infinitely large, infinitely detailed, because it's just described by mathematical functions. So unlike things like fields, where you have a really tight limitation on the size and detail possible with a field, or particles, where in order to make something bigger, you need more and more particles, which takes more and more data, or meshes, where to make them more detailed, you have to make more polygons and so on. With procedurals, there's no concern about that. They can be unlimited in size, unlimited in detail, and that doesn't really cost anything. So then what actually happens when you make a procedural? So you have a procedural root node, and it has a load of nodes attached to it. So you attach your primitive nodes to the procedural root, so on. And when you do this, the procedural root node underneath generates some code. It generates a little bit of shader code. And that shader is capable of evaluating the functions for that node to find the signed distance. And then once you've got that bit of shader code, then you can use it to do all sorts of things. So you can generate a mesh just by finding all the areas of space where the distance is 0 and putting polygons there. Or you can use it for a field by saying all the points inside where the distance is negative, you put some stuff in the field. Or particles, you just emit particles wherever the distance is less than 0, or so on. And you can use them for collisions, because obviously if you're trying to find how far a particle is from the surface, you can just sample the distance. You know where it is. So it's really, really useful and powerful. So what does a signed distance function actually look like? So this is the signed distance function for a sphere. So there's a bunch of generator nodes in the procedurals tree, node list in Notch. And one of them is called editable code. Has anyone ever touched that node? Like one or two people. So if you add the editable code node into the graph, and then you type that into the editable code node, and then you put a procedural meshing node on the end, you'll get this. Or you could just add a primitive sphere. But the point is you can you can type code and stuff comes out. It's amazingly. You can generate random stuff just by typing in things, as long as the stuff you type in is valid and not garbage. So anyway, what does this function mean? This means that for every position in space, I evaluate this, and where the value you get is 0, it puts polygons. So in this case, the function is the length of the input position, which in practice means the distance from world 0 minus 1 equals your distance. And minus 1, so this means the distance minus the radius is the distance from 0 minus the radius gives you your sign distance. So logically, that gives me a sphere of radius 1. Okay? Bear with me. So now what if I want to move the sphere to the right, to the left? If I want to move the sphere to the left by half a unit, how do you move the sphere? So in this piece of code, I've moved the sphere to the left by adding 0.5 to the world space position. This seems counterintuitive. I've moved it to the left by moving the sphere to the right. Why is this? And this is a really core thing you have to understand about procedurals. You never move the sphere. The sphere doesn't move. You move space. There is no spoon. You don't think about bending the spoon. You think about bending space around the spoon. So I've not moved the sphere at all. What I've done is offset space so that space has shifted, and therefore when I generate a sphere at 0, it now appears to be in a different place. And once you understand this simple but really critical point, then everything about procedurals becomes clear, and you can start doing really odd, crazy things with them. So now I want to stretch the sphere. I want to make the sphere 4 times wider. So how do I make the sphere 4 times wider? I make the space 4 times narrower by multiplying the space by 0.25. So I've shrunk space, and that gives so by compressing space, it gives them the appearance of the sphere being bigger, right? Okay, so far transform's not particularly interesting. What if I want to repeat the sphere infinitely, forever, in space? So I can repeat a sphere infinitely just by repeating space around a small point. So instead of saying that space goes on forever in that direction, I actually say space only exists around the sphere, and I just tile space. So now, when I evaluate that, it gives me the impression that the sphere just goes on forever, because actually I'm just repeating space. And you can see the relevance to this when you start talking about trying to make something really big and detailed. If you can do things like manipulate space in such a way, then it obviously kind of makes sense why this is interesting. Okay, let's try something else. I want to warp the sphere. So how do I warp the sphere so it appears rippled? Well, I don't warp the sphere, I ripple space. So by making the space warp up and down, when you evaluate a sphere in a warped space, the sphere itself appears warped. And then how do you combine? So you can combine shapes. The CSG means constructive solid geometry, for those who've been in graphics longer than like 20 years. Or Boolean operations is the other way of thinking of them. But this enables you to combine multiple procedural shapes. And in practice, what it does is it just takes the distance from one shape and the distance to the other shape, and it performs a mathematical operation to combine the 2 distances. So a union of 2 shapes is just say you take the distance to one shape, the distance to the other shape, and you take the minimum of the 2. And subtraction is you subtract the max. I can't remember. And I think intersection is the max. And there's a bunch of formulae for all of these. And if you Google sign distance field Booleans, you can find all the code on the internet, because this is quite a common thing. And there's some quite interesting things you can do. We support a bunch of standard things like union and subtraction and some smooth operators. But if you go online, you can actually find people who have done code that makes two shapes look like they combine in staircases, or smoothly chamfer, or bevel, all this kind of thing. So there's really powerful things you can do just by combining shapes with some clever mathematical operations. So now I'm going to go through some use cases of procedurals that are not immediately obvious. And then I'm going to go through how you model some stuff with procedurals. Okay, so some procedural use cases you might not have thought of beyond making meshes and so on. You can use them to emit fields. So one of the great things about procedurals is you can turn loads of stuff into procedurals in the first place. Like, it's relatively easy to turn a mesh into a procedural, or particles into a procedural, or combine those things. So you have some particles with a mesh cut out of it, and so on. All these things are very straightforward to do. So once you've done that, you can use what you've made as an interesting way of emitting things like fields. So here I've got some blobs, and I can just emit that straight into the field. I get this kind of shape just with a field procedural emitter. And I think I've got the wireframe, you can't really see it, and this one. And then I can apply turbulence to that like a field. So it's a really interesting way of emitting shapes. You can use them as rigid body colliders for rigid body physics, which I cover a bit more in detail in the rigid bodies session later on this afternoon. So some things make really good colliders for physics, like primitives and closed shapes. And some things make terrible colliders, like any other mesh, really. But procedurals make excellent colliders because they are solid. You know the distance, you know if you're inside the shape because the function tells you. So you can easily push the shape back out so it doesn't fall through. Really useful. So here's a quick shot of some cubes like falling around the procedural. Something you might also not be aware of is that procedurals can be used to do custom fall-off shapes for clone effectors and particle effectors. So here's an example of using a cloning system just with a plane effector, but using the procedural system to define the fall-off for the plane effector. So if we just have some clones emitted in a radial fashion, and I've got my procedural, which I've rendered as a mesh, and then I apply a plane effector, just straight plane effector, and link the procedural into its fall-off, then you can get this kind of custom shape to the fall-off. And there's the node graph for that. So you can see you've got the procedural just going into the plane effector's fall-off. So when you want to do strange things, like maybe you want a mesh to push out of a cloning system, you can just do that with the procedural custom fall-off. Procedurals, so you can use procedurals as shading. I don't know if anyone's ever looked at the shading nodes in Notch, which allow you to do generative shading on objects. But here's an example using procedurals for that. So this is actually just a bunch of planes cloned. So you just get a plane, clone it vertically, and then you use a procedural shading node attached to the material of the planes. And that defines an alpha mask per pixel in space and maps it to a procedural. So here's the node graph for that. So you can see I've got just a cloned plane with a material going into a procedural with a procedural shading node attached. And the procedural shape just goes straight into that. And then there's some other stuff in that scene, like particles that you don't need to worry about. So now we're going to go through an example of how to model stuff using procedurals. So procedurals can be used for like basic, non-destructive, solid modeling in Notch, just by taking multiple shapes and combining them together. So here's an example made by Adrian at the back there, who will surely answer questions about it if you want. About how to model a chess piece just using procedurals in Notch. And this is step by step. So the first step, we've got a plane, and we use just a cylinder shape on the plane. You can see the nodes as I build them up. So I'm going to add another slightly smaller cylinder shape, just with another union. I will allow people to take pictures as they not go too fast. And then we're going to add another cylinder shape, but use a smooth union so that kind of blends in at the bottom. So the key thing with procedural Boolean operations is that the vertical order is obeyed. So you're blending something on top of the stuff after it. So this is smooth the union in with the two shapes below it. And then we've added a torus with another union to create this kind of bottom shape. Now we've got another torus that's smoothly subtracted to give this kind of soft curve to the piece. And you can see how that's affecting the area. That's the area where that torus is affecting the stuff below it. Now we've added another torus, just smoothly unioned on top to get the kind of extruded shape there. We add another one at the top. And yet another one. Kind of see where we're going with this now, isn't it? It's a bit of a Tony Hawk kind of, can you see what I did? And then we got another sphere which is subtracting a kind of an indent in the top. And then we've got another torus cutting in. You can see how that's cutting in there. Now we've got something a bit tricky. So we take a sphere and we do a mirror so it radially repeats the sphere in X and Z. So you have a slightly offset sphere in the left, and that's mirrored to give you a look of 4 spheres. And that is subtracted from the whole thing. So the important thing is the sphere is parented to the mirror node, and the mirror is the one with the Boolean operation that makes it subtract. And you see how that is applied to the chess piece. So it's cutting in the little crown onto the chess piece. And then we cut another sphere in to deepen the crown and give the detail. And then we add another sphere on top. And another one with a smooth union, like this blobby one. And that's the final graph. So you can see just by simple primitive shapes with clever Boolean operations and smooth operations, you can make something quite decently complicated. I'm not sure why you do this necessarily, but you can. It's a good exercise. Obviously, you can save this out as a mesh, so that's something. And here's how it looks rendered. So we've actually put some, and Adrian's gone and made another one, just to have a nice pair of pieces there. Presumably, he just put a couple of boxes with a smooth union, I'm guessing, is that? Yeah, right. OK, so what do you do if you want to texture this mesh? So one of the problems with procedurals is that signed distance fields don't have UVs because there is nothing to UV. There's just a mathematical field in space. It's not like you can, it's not an easy way to UV map that. So the way you end up texturing those is by using a mapping node. So in this case, we've just done, what type of mapping is that, Adrian? What type of mapping? Is it cylinder or box mapping? Okay. Yeah, so it's a cubic mapping on the mapping node. And just applying a texture. And you can see here's the graph for that. So the texture is also generated, fractal noise with a color ramp, and then A normal map is generated from that. So you've got a normal map that matches the texture. And they're both applied to the material node. And that gives you this kind of generated shape. So UVs you can't really generate, you have to generate UVs. They don't really carry with the procedural. However, colorization is now possible in 922. So I've got this procedural shape here that Ed, one of our guys, has made. And if you look here, you've got a few toruses with no blending, kind of just unioning themselves together. And we've now added the ability that for each procedural shape, you can assign them a color, and these carry through. So if we assign a color to each of those, you'll see that there's a very obvious colorization. But the intersection between those shapes isn't particularly nice. It's just a hard cut. However, the interesting thing is that the colors obey the same Boolean blending as the shape. So if we change the union to a smooth union, you get a smooth color blend as well. So it enables you to do a slightly nicer job. And this is kind of an example of a bunch of things where they've been colorized. So, and the node graph for that. So he's just kind of applied some. So that's actually, they're using images as part of the procedural to emit the star shape, and then just colorized each of the primitives. So now the next thing, I want to get on a slightly more involved example of how you use procedurals to model clouds. Clouds are like one of the worst things to do in computer graphics that you can possibly do. They're horrendous. They combine like the three most horrible things about graphics that you can do. Because clouds, they need to be really massive, like infinite. Like they need to seem to go on forever, so they're huge. But at the same time, they're really like infinitely detailed as well. So it's like there's no trade-off of size versus detail. They need to be both huge and really detailed. And they're also transparent. And they also need to be lit properly to look any good. So all the bad things about computer graphics combined in one thing. And there's a bunch of ways that you could try and make clouds. So has anyone tried to make clouds in Notch? How did you try it?
Truly, I don't remember. Maybe not noise, but kind of a tree space, and then trying to use some field to give it like a...
Yeah. Because if you do, because this is the problem, like you do fields, and like you can make a small cloud, and then you try and, but it's like one cloud. You can't do like a skyscape in fields. And if you do particles, like you can put some, like a cloud shape on a particle, but it ends up not really having any lighting or detail. So yeah, there's no really good solution, but procedurals can be a really good solution to model clouds. So how are we going to do this? Probably it's going to involve a decent amount of noise and fractals, and probably some like artistic guidance, because the naive way to do clouds probably is just to stick a fractal noise, and that's it. But this doesn't really look like anything. So ideally, what we want to be able to do is actually have like creative, artistic guidance on modeling the clouds, so you can define some key shapes in a creative, an artistic way, and then use some noise to fill in the details, perhaps. So I'm going to show how I've done some cloud modeling in Notch. So the first step is to take just some 3 sphere primitives. So I've got 3 spheres and combine them using smooth union. So you get this kind of blobby shape. And the next thing I do is I repeat this shape infinitely, just by using, so the node graph for this is here. So I just used a repeat node to tile the three spheres infinitely in X and Z. So that's now infinitely tiling. And that's one part of the cloud. The next thing, so now I'm going to go back and start with do something else. So for this is a plane, just a plane in Y, which I've rotated slightly. And then it's been displaced with a number of noise functions. And this was all editable code node. So I've opened up the editable code node and typed in the equation for a plane, which is very simple. And then I've warped space around it to give it a bump. And here is the code for that very thing. So the equation for a plane in 3D space, is like a plane in Y, is just the Y component in the position. That gives you already the distance to the plane. So if I bump space, if I warp space in Y around it by using a sine function and some noise functions, then it has the effect of warping the space. And these numbers are completely arbitrary. I just like fiddle around until you get something that looks decent. So that gives me my warp plane. So the second thing I'm going to do, again, a completely separate thing, is so I just made a sphere and repeated it in X and Z. And then I warped the space in a kind of a nice way to give a sort of a noisy, non-repeating look. It's quite easy to make something that doesn't repeat. You just have noise patterns that don't repeat, and you get something that never repeats. And this is another editable code node, and here it is. So I've offset the space, and so I bump it a bit, and then I offset it with a sine wave, just a sine deform on Y. And then I offset the X and Z using just a simple repeating pattern. So the third line there, the GLSL mod, that is what makes space repeat in X and Z. It just says, instead of going on forever, only consider this, repeat this portion of it. And then the last line is the distance to sphere equation, which you might remember right from the very, very beginning of this presentation. So if you take this shape, and then you glue them together, you get this shape. It's sort of slowly becoming something. So all I've done now is I've smooth unioned the first two things that I've made. And this is kind of giving me my sort of bumpy base cloud layer. And then I add on the other thing I made with the repeating spheres. And what I've tried to do here is is having a noisy base layer with some sort of bumpy elements, and then added the spheres as a kind of cumulus, like extruded shape. And it kind of starts to look like, I wouldn't say it necessarily looks like clouds, but if you squinted and imagined it was more detailed, you could start to make it look like clouds. So the next thing I want to do is actually add details, like fine details to this. So now I'm going to start adding noise. And this is just, there's an FBM node in Procedurals, which just basically just warps space with a noise function. So everything you apply, if you apply that to your graph, then everything looks more noisy. And there's also a cells function, which makes things it's like the combination of those two things together gives you quite a nice, like cloudy, noisy look on top of like the overarching main things you've modeled. And now I get something that looks like clouds. So I could jump ahead and show you the final render, but you'd think I was lying. So I'm not going to do that. Instead, I'm going to go back and show you the same things again, but now I've applied the actual cloud shader to them. So if you use the volumetric tracer node in Notch, it does basically like a volumetric ray trace of the procedural, but it's capable of applying light to it, like soft absorbed light. So you can hook a couple of lights to it, like hook a directional light to it, and it's got some scattering function and soft shadows and so on. So I take the very first thing I did and I apply and render it with the volumetric tracer, and now I get something that's a little bit more sky-like, and I put a gradient in the background. So following through from that, I added, so I put back the other elements, I've combined the other elements, and yeah, I've moved the camera as well. And now, this is the first piece of noise I add. So this is a cellular noise, and you can see it's got a really obvious repeating pattern of basically just bumping the whole cloud in a kind of like blobby way. So it's made it look a bit more like, if you were being generous, you could say it's made it look more pyroclastic, and if you were being honest, you could say it's a little more blobby. And then if you add FBM on top of that, then you've got something now that looks quite decently detailed. And then if you go and color correct and fix the camera angles and everything, and then you actually end up with like quite a reasonable volumetric cloud. And the nice thing about this is you can fly around the scene forever. So if I put a modifier on the camera, or if I dare to say it, if I keyframed the camera, then you could fly through this infinitely. It's because it goes on forever, because it's a repeating pattern, it's not bound. And you could continually add details and make it more and more, make it more interesting, or you could bring in a few elements that are actually like, if you want to put a face in the clouds, you would add a procedural mesh and comp it in. And here's the shot from the thing in the actual, the way it was actually used. So we, in this case, we also put some meshes in the scene and some flares and particles and various things. And there was a camera fly through. So this is kind of a reasonable way of modeling clouds procedurally. So finally, I want to talk about some of the issues you have with procedurals and how to overcome them. So you might have noticed if you've been using procedurals and you, like maybe you had like a fractal noise you were turning into a mesh or something like that with a meshing node, or particles, you might have noticed at some point you get holes in the mesh. And you're kind of wondering why you get these holes. So in theory, a signed distance field is meant to actually give you the closest surface, the closest distance to surface to any point in space. That's what it's supposed to do. That's the contract it has with you, right? And this is called the Euclidean distance. But all the things you can do to procedurals to make them interesting, like warping them and putting noise on them and stretching them and so on, they mean that the distance the function gives isn't actually the closest distance to surface anymore. It starts to drift. It's starting to be wrong. And the wrongness of that is what gives you holes, because it's meant, when it's trying to find the surface, it misses the surface. It gets it wrong. And generally, the further you are away from the surface when it's trying to find the distance, the more wrong it is. So we have a parameter. Well, there's two ways of fixing this. The right way to fix this is you go back and fix all of your equations so they actually give you the real distance. And this is really hard and not worth doing. No, we're not going to, that doesn't work. We never figured it out. So you could do this, but it's not really possible. So the workaround is that procedural rendering nodes have a parameter called error tolerance. And because the way all the procedural rendering nodes work is that they try and rapidly find the surface, like by using a search. So they say, here's all the space that I'm interested in. I want to do a rapid, like, finding the zero distance by like a binary search or something like that. And the error tolerance parameter, it makes the search more fuzzy. It makes it more able to find, it makes it search harder. And as a result, slower. But it means that it will be less likely to miss the surface and give you holes. So if you up the error tolerance, you can get around this problem. So that is the end of the slides. But if anyone has any questions, please, yeah.
I think the procedurals are limited to some kind of amount, like resolution, 512, I believe.
It's only the rendering nodes that are limited. Now, the procedural itself is not limited, but the way it's rendered is limited. Like you can only do a certain resolution of mesh or something. But this depends on the rendering node. Like the volumetric tracer node doesn't have a resolution. It just does it as a ray trace, so it's not limited. So it's all dependent on the system.
Following up on that, would there be a workaround to that limitation on the rendering node resolution?
Well, I mean, you can, because the nice thing about this is like you can have a rendering node that follows the camera around. Like it doesn't have to be locked in space. It can move. Or you can have multiple render nodes. Like you can have one in the middle that's really high res around the camera, and then stick another one next to it, which is lower res and bigger. So it's where you put detail where you need to see it. So yeah, it's all just looking at one big procedural space. It's just how you decide to visualize it.
How much time does it take you to come up with the concept of doing the cloud? Because seeing your slides here gives me the impression you have been sitting there for 2 hours, but obviously you haven't, right?
I've been here before. This is not a notch thing at all. This is a technique used heavily in, like Houdini does this. If you go online and go on Shader Toy, have anyone heard of Shader Toy? Like most of the examples on Shader Toy are using distance field techniques. I'm not saying you should do this, but obviously the many inspirations can come by going on Shader Toy and trying to work out how their stuff works. And the code's there, and you can kind of try and see what happens when you do it in Notch. It takes a bit of understanding because in their samples, they're kind of combining rendering and generation. But if you can figure out the part of the scene where they're generating the shapes, like there's some artists in the world who exclusively use these techniques. Like this guy online called IQ, who you might have heard of. He models insane, like Pixar-like characters entirely just with distance field techniques. So yeah, there's a lot of reference out there. Yeah.
In your cloud, you've got the GLSL call. Does this mean that you can use the shader GSL.credit?
No, it's not. It's all HLSL code. It's just there's a function. The reason is that the modular function in HLSL and GLSL work differently, so we give you both because the GLSL one is more useful. So we just made a version of it for each. Yeah.
What's coming next for procedurals and releases?
We added color support. We have. I don't know if you've seen the reaction diffusion. I think this was in the last release, but. So this technique was added reasonably recently. There's more work going into other areas of the software. There was a lot of stuff went into procedurals in the last release. This is a really heavy boost to procedurals. So there's less in this release, but we'll probably be adding more things in the future. Like, I mean, it's kind of, so if you think of it as just one big continuous function, not as a mesh, like the reason colors work is because it's just a value, right? But with materials, like, and you can blend the color values, you can seamlessly blend them. With materials, you need to actually have an ID, like a hard cut. So it doesn't make sense in the same way that colors and positions work. That's why there's only one material. It can only be one material. It's just kind of how it is. It's like there is only one material because there's only one shape. It's kind of an awkward thing about it, I guess. Is there any other questions?
Is there a way to make two, between a mesh texture and rig and talk about it? Or like, gluing it together? Is there like a
No, not really. No. I think maybe there would be, what we'd probably have to do is have a way of like defining areas of space that were used for different materials or something, but it would be quite rough. It would be hard to specify. Yeah.
At table code node is not giving any output if you mistype something. Can you suggest some idea how to test your code?
The log window should give you some information. The log window should give you some error information, hopefully. Any other questions? Good. Thank you very much. Cheers.